Hi, my name's Mark. I'm here to help you with your GCSE and A-level maths studies. This is a live stream to help you with your maths problems. It's my office hours live stream that is on every week. This week's topic we have been looking at partial fractions. This is in the A-level course of the content and towards the second year material, even though a lot of schools usually teach it at the end of year 12 to get a head start on the year 13 content. That is what we've been learning this week, but as always I'll open up the chat halfway through and we can go through as many questions as you like on A-level or even GCSE type questions. But firstly, what we will do is have a look at this starter question. The starter question is based on it's on two different sections. It's on the exponentials and logarithms section, and also it's on the proof by contradiction section. So let's have a look what we've got here. So it wants us to show that log 2 3 equals p over q implies that 2p equals 3q, or 2 to the power of p equals 3 to the power of q. So what I will do is write the first step. If it's a show that question, you want to start with the left hand side and eventually get to the thing they are implying. So let's have a look. So log base 2 3 equals pq. That's what they've started with. If that happens, then if we times both sides by q, we will have q times log 2 base 3, log base 2 of 3 equals p. Now this is where your first year exponential and logarithms knowledge comes in, because you need to know your laws of logs. And this is the power law of logs, but it's actually in reverse. Usually you used to bring the power of 3 down. This one, we can bring the power q up. Okay, so you have log base 2 3 to the power of q, and that equals p. Right, then what we can do on both sides of the equation is we can remove the log base 2 by using its inverse. As we know, the inverse of a log is an exponential, but it tells us what base number we have to use because it's log with a base 2. That's what the little 2 refers to. We have to do 2 to the power of the left hand side and 2 to the power of the right hand side. So the 2 to the power log base 2 cancel each other out because they're inverses, and you're left with 3 to the power q, but you also have to do 2 to the power of the right hand side, and that equals 2 to the power p. And that is what they wanted you to show. 2 to the power of p equals 3 to the power of q. Right, that's given you a hint for the next part of the question. But the next part of the question wants you to use proof by contradiction. And we need to prove that log base 2 of 3 is irrational. So to do that, whenever we are doing a proof by contradiction, you always assume the opposite to the statement you've been given. So what I would suggest you do is always write a statement at the start, assume, and tell the examiner that we are using a contradiction, that we know it's going to lead to a contradiction at the end, and so we are using a by contradiction example. So assume for contradiction that, and they're asking you to prove that log of base 2 3 is irrational. So we need to assume the opposite. Assume for contradiction that log base 2 of 3 is rational. Now what does rational mean? Well, it means it can be written as a fraction. So you would put log 2 of 3 equals, and you could put P over Q like they've done in part A, but I'm going to put A over B, but you need to explicitly state what A and B are, because if they are decimals then A over B would not be a fraction. So what you'd put is where A and B are integers. You could even say they are integers with no common factors, which does help you in some of the proofs when you're proving surds or irrationals or prime, and there are infinitely many primes later on in the course. But for this proof, it doesn't actually matter if A and B have no common factors. In other words, the fraction is in its simplified form, because that doesn't lead to a contradiction. Right. So the idea is, because this statement says, log base 2 of 3 equals A over B, okay, you could put then by part A, this implies 2 to the power A, because P was the numerator, so yeah, 2 to the power A equals 3 to the power of B. Now, this is an obvious contradiction if you know about the fundamental theorem of arithmetic, which basically you've done it at GCSE, and it says every integer can be written in a product of prime factors. This number can be written as 2 to the power of an integer, and the other number can be written as 3 to the power of an integer. They are both primes, 2 and 3. But the thing about the fundamental theorem of arithmetic is this factorisation has to be unique. So the idea is you can't write a number as 2 to the power, and you can't write the same number as 3 to the power, okay? But if you don't want to use the fundamental theorem of arithmetic, then you can look at that and think, okay, if A is not equal to 0, then the left-hand side is divisible by 2. In other words, the left-hand side would be an even number if A was not equal to 0. Okay? And clearly on the right-hand side, because B is an integer, it's a multiple of 3. 3 times 3 times 3, which is a multiple of many odd numbers. So it cannot be even, because an odd times an odd is always an odd. So the idea is the left-hand side is divisible by 2, okay? The right-hand side is not divisible by 2, because it's an odd number due to the prime 3 being multiplied by itself. So if you saw that, okay, that suggests to me that A has to equal 0, otherwise this wouldn't work. It would lead to a contradiction in that place. Okay, so that would lead to a contradiction stating log 2 of 3 is not rational, like our assumption originally claimed. It needs to be irrational. Okay, but also be aware that what happens if A is equal to 0. Okay, so that gives you a contradiction. But also consider all possible cases. Okay, so if A does equal 0, then 2 to the power A, or 2 to the power of 0, equals 3 to the power of b. In other words, 1 equals 3 to the power of b. And what we come down to is a has to be 0, but also that would imply b has to be 0, because the only way 3 to the power of something can be 1 is if b can equal 0 as well. So in other words, the only way 2 to the power of a equals 3b is if both a and b equals 0. Why would this be a contradiction? Because yes, they are both integers. The reason why it was a contradiction, and you might as well have written this earlier, a and b are integers because a over b would be a fraction, okay? But a could be 0, yes, that's absolutely fine. But b cannot be 0 because it's the denominator of a fraction. So maybe when you go up, and the examiner will not know this, but instead of saying no common factors, you could have put, and I'll write it, okay, a and b, because you don't know at the end of your proof what is going to cause the contradiction. A and b have no common factors in your assumption. And you could put b not equal to 0. And that's where the contradiction comes, because you can't have 0 divided by 0, for a and b cannot both be 0. So that contradicts, and what does it contradict? I always say what your contradiction is. It contradicts that a over b is a fraction, since b cannot equal 0. And then when you finish with your proof by contradictions, what I would always suggest you do is always write at the very end the statement that's true. So you've stated where your contradiction is, which is good, and then you'd put hence, again, by contradiction, what have we proved? We have proved log 2 of base 3 is an irrational number. Because when you're doing proof by contradictions, what you're always assuming is you assume the opposite. If that opposite is true, then you get to something that's clearly incorrect based on the knowledge you originally have. So that means your original assumption is false. And if you want to put that original assumption is false, you can do. So first assumption is false. Hence, by contradiction, log 2 of 3 is an irrational number. That's a bit of practice, and you will see that when you come to do proof by contradiction, either at the end of year 12 or at the start of year 13, depending where you are in the course. But there will usually be, the majority of the time, you usually see at least one proof question on each paper. You may see a proof by contradiction, but also a first year proof deduction, exhaustion, or disproved by counterexample. So, the next question we will do, and it's probably the one you've all tuned in for, is the one that's posted on Instagram, because that is the partial fractions question, or the puzzle for this week. Can year 13 students actually write this in partial fractions? First things first though, you have to be able to look at it and think, how do you set it out in partial fractions form? Because you will not always be given that. And the reason why this is tricky is because you look at 3 different important things you need to see in the fraction first. You look at the original factors on the denominator and see, is this a repeated root? For instance, do 2 brackets or 2 linear factors appear more than once? And also you need to look if it's improper or not. Now, sometimes you may not be able to split the denominator factors into linear factors, and let's see if we can do here. The x minus 1 is linear, but the 4x squared minus 9 is, or can be, split up into linear factors, and this one is called completing, sorry, not completing, it's called the difference of two squareds. So the denominator can be split up into 2x, because that's the square root of 4x squared, plus 3, and then 2x minus 3, and then the x minus 1. Because 2x plus 3 and 2x minus 3 multiply together to become 4x squared, because they're conjugates one another, one's a positive, one's a negative of the same numbers. The middle two terms cancel, and the plus 3 times the minus 3 will become the minus 9. So first of all, try and factorise the denominator as much as possible. As we can see, there's no repeated roots in this question, but because the denominator is a cubic, because you're timesing a quadratic by a linear to get a cubic, and the numerator is also a cubic, what you will find is it's actually classed as an improper algebraic fraction. So the form you will have to express in partial fractions form is, when you do a cubic divided by a cubic, you get a constant. If you're doing cubic divided by quadratics, you would get a linear, because you have x cubed divided by x squared is x's. But because you're doing x cubed divided by x cubed, what you would get is a constant number. So you have a. Then the other, or the remaining partial fractions would be just simply constants over each linear factor. So you have b over 2x plus 3, c over 2x minus 3, and d over x minus 1. So that's the form you need to be accustomed to. There's 3 different types. You can have improper fractions, you can have repeated roots, or you can have the simple ones where you just split it up into each individual fraction over the individual linear factors. But always remember which one to use in case they don't ask you, or ask you to show that it can be written in this particular form, because then you will know. If it's a show that question, then you know the form it has to be written in. So as with always partial fractions, with all partial fractions questions, the next step is you'll multiply through by the 3 factors on the denominator. And what you'll be left with here is 10x cubed plus 15x squared. And that would equal a times, and then you will times by every single bracket. 2x plus 3, 2x minus 3, and x minus 1. Then the b fraction will also be multiplied by every single bracket, but the 2x plus 3 would cancel on the numerator and the denominator, so it would just be left with 2x minus 3 and x minus 1. Similar for c, but the 2x minus 3 bracket would cancel, 2x plus 3 and x minus 1. And then the d, the x minus 1 bracket would cancel, so you're left with d times 2x plus 3, 2x minus 3. Alright. So the next stage, as we say, there's 2 usual methods. You can either sub values in that make the bracket 0. So you could sub in x as, say, 1, you could sub it in as 3 over 2 example, or you could use comparing coefficients. It depends which technique you want to use, but comparing coefficients method here is actually easier to find your a straight away. So always compare the highest power. So let's say compare coefficients of x cubed, because the highest power on the left is an x to the power 3, and the highest power of x on the right is x cubed also. Right, so on the left hand side you have 10x cubed, so on the left you would have 10, and on the right hand side you can do a bit of multiplying out the brackets, but the D bracket will just become a quadratic, the C bracket would also become a quadratic, same with B, so the only actual x cubes you get are from the ones that multiply by A. So if you multiply those brackets out, you're only interested in where the x cubes come from, and that would be your 2x times your 2x times your x. So it would create 4x cubes. So you'd put 4a. And that implies a equals 5/2. Just to see where that came from, I will zoom in on this bracket. What we're doing is if you multiply these triple brackets out, you'd have 2x times another 2x is 4x squared, times the x is 4x cubed. So then when you times it by a, you would get 4a x cubed. Okay. Obviously there'll be more in that bracket, there'll be x squareds and then x's, but I would always look at the highest power to see if you can find any constants initially. Right, so let's continue. You could compare coefficients of x squareds, and you might have to in certain problems, but for this one I would advise just subbing in x values, because you would have to multiply out your triple brackets to see how many x squareds there would be for A. Similar for B, similar for C, similar for D, you'd have to have x squareds in each of them. So don't compare coefficients anymore, try and choose the x values that make the brackets 0. So let's choose x equals 1. So you would have 10 times 1 cubed is 10, plus 15 times 1 squared is 15, and then add the 10 and 15 would be 25. Now the reason why I've chosen x equals 1 is because when you sub it into the x minus 1 bracket it disappears, so a times 0, b times 0, c times 0, and you're just left with d times 2 plus 3 is 5, 2 minus 3 is minus 1. So what you're left with there is minus 5 times d is 25, so it implies d equals minus 5. Right, the next value I'm going to choose here is where 2x minus 3 equals 0, so add the 3, divide by 2, so x equals 3/2. And then what you would do is use your calculator, because you get a calculator in every single A-level exam paper you face nowadays, and you substitute it into both sides. So 10 times 3/2, sorry, cube it, and then plus 15 times 3/2, and then work with me here, see what you get, see if you get the same. If you want to pause the video and give it a go yourself, that's even better. See if you get the same answer. And then what you would do here is get 135/2, which is the left hand side. So 135/2. And what does that equal? Well, the nice thing is when you sub it into the right hand side, you can ignore the A, ignore the B, ignore the D, but the C bracket will not be 0. So 2 times 3/2 is 3 plus 3 is 6. 3/2 times 1, sorry, take away 1 is 0.5. And then what you would have is half of 6 is 3. So it implies C equals, when you do 135 over 2 divided by 3, you get 45 over 2. There's one more x value to sub in, and that would be minus 3 over 2. So if we do it again, just like we did before, minus 3 over 2 cubed, and then plus 15 times minus 3 over 2 squared, you actually get 0 on the left hand side, which is nice. Because 10 times 1.5 cubed, 135 over 4, and 1.5 squared, that's 15, is 135 over 4. So you get 0 on the left hand side. So the right hand side must be 0 as well. So if we're looking for the brackets without a 2x plus 3, that would be the B bracket. Minus 3 over 2 times 2 is minus 3. Minus 3 is minus 6. And then x minus 1 is minus 3 over 2 is minus 1 is minus 2.5 or minus 5 over 2. Doesn't actually matter what those values are, because when you do 0 divided by them, you get b equals 0. Now there may be some instances, just like this one, where you do get one of the constants to be 0. So what we will do is just always write the final answer on the final line, and how we write 10x cubed plus 15x squared over 4x squared minus 9 times x minus 1. If we're looking at how this is to be written, will be equals 5 over 2 is your constant term. You don't need to write the b over 2x plus 3 because b is 0, but you write plus 45 over 2 over 2x plus 3. That's your c. Sorry, you don't have a over 2x plus 3. That would be your 2x minus 3. Just be aware. Mistakes are easy to be made when you're doing so many arithmetic puzzles in your head, but it's how you deal with them under exam pressure. Just go back and make sure you correct any errors. It's one of the big skills you learn, not just your mathematical skills, but how to keep calm under pressure. And then minus 5 over x minus 1. So that would be how you write it in partial fractions form. Right, so what we're going to do now is I think we're going to do an exam style question that's been asked in the past on not just partial fractions, but it gives A-level students an idea of how to solve binomial expansion questions using the topic. Right, so I've just changed it over, and I know I forgot to change it over on the question above my head. Apologies for that, but hopefully because you could see it on the whiteboard, you could see the question already, and people who have come over from my Instagram would have seen that question already. But now I will show the exam question so that you can have a go at this also. So let's continue with this question. This is from the A-level paper. It was in November 2021, so there was no summer exams in 2021 because of the pandemic. And it was in November, and it was on paper 1, it was question 9. So let's have a go at this particular question and see how we get on. If we notice for this question, you have 5x plus 2 squared, and you have 1 minus 2x. They are the denominator factors, and as we can see, one of the brackets is repeated. So this is the repeated root case. So you get 3 individual fractions, and you get 1 with 5x plus 2 on the denominator, and 1 with 5x plus 2 squared on the denominator, just like it says. And if you notice, it's giving you the form you need to write it in. So unlike the previous question we've tried, it's giving you a hint on how to write it. The reason why you don't have to worry about the improper case or the quotient at the start of the fractions is because this time we have a quadratic, 50x squared, divided by a cubic. So the numerator is a lower power than the denominator, which is absolutely fine. So, as always, we multiply through both sides by the denominator, and what we would get is you would get 50x squared plus 38x plus 9, and that is equivalent to, when you multiply through by the denominator, a times the 5x plus 2 bracket would cancel, but it would still leave the other 5x plus 2 bracket. 5x plus 2, 1 minus 2x. Then you would be left with add b. Both 5x plus 2 brackets would cancel, and you're only left with 1 minus 2x. And c, the 1 minus 2x bracket will cancel, but you leave with the 5x plus 2 all squared. Alright, so the next step, what you would do, is, as always, you can sub in x values that we will do first here, or you could compare coefficients. It doesn't really matter which one you choose to do first, but let's sub in x equals minus 2/5. So let's do x equals minus 2/5 first. And what you do is 50 times 0.4 squared plus 38 times minus 0.4, which is minus 2/5, and plus 9. So the left hand side would be 9/5, and the right hand side, it would only be considering the b bracket, because the others get times by 0 when the 5x plus 2 bracket becomes 0, because x is minus 2/5, and you have b is times by 1 minus 2 times minus 0.4, and you get 1.8 or 9/5. So the nice thing here is b. This implies b just equals 1. Perfect. I don't think I did this last time, but always, once you've finished an exam question, go back and circle the important parts of it, because it makes it easier for the examiner to see where your actual solutions are. Right, so let's sub in, what have we got here? X equals 1 minus 2x is 0, so 2x is the same as 1. So x equals a half. Let's make that x a bit curlier to see what it looks like. So once you've done that, let's sub it into the left hand side. So you have 50 times 0.5 squared plus 38 times 0.5 plus 9. 81 over 2. Right, so now you sub it into the right hand side as well and see what you get. Some of the brackets cancel, you're left with 5 times a half is 2.5, add 2 is 4.5, so you've got 9 over 2 squared. 5 times 0.5, add 2, and then square that. 81 over 4, that can be written as 81 over 2 equals c times 81 over 4. The 81s on both sides cancel, and you're just left with C to B. Yeah, C to B equal to 2, I believe. I'll just check it. Yeah, that's the one. So it implies C equals 2. So as said, you've used both brackets now, the 5x plus 2 and the 1 minus 2x. You can sub in x as 0, but the more sophisticated way, and the way that would help you when you come to do the improper examples as well, will be, let's compare coefficients of the highest power. And here, the highest power is your x squared, because x squareds are on the left and x squareds are on the right. Just start with an important fact that you choose the highest power that's on either side. So even if there may only be x's as the highest power on the right, but quadratics on the left, you still use the x squared. And likewise, if it was only a numerical value like the 9 on the left and x squared's on the right, you would still use x squared because that's the highest power throughout the total identity, or the equation if you like. Right, so on the left hand side we have 50 of them, 50x squared, so we'll put 50x squareds there, and that has to equal the same amount of x squareds on the right hand side. Let's just go and look at the right hand side for a little while. Okay, 5x times minus 2x, that becomes minus 10x squared. The rest of the multiplying out of brackets doesn't matter because we're only interested in the x squareds. You don't get any bx squared, okay, because that would just be linear. Oh, just be careful, you'd get c here, because when you multiply 5x plus 2 times 5x plus 2, you get 5x times 5x, which would be 25x squareds. So, putting that together, on the right hand side you would have minus 10a x squareds, but also you'd have plus 25c x squareds. Now, because we have already found c to be equal to 2, we can now write 50 equals minus 10a plus 25 times 2, which is 50. We're going to come into the situation again, I think, where a would turn into 0. Yeah. And so that students, 0 equals minus 10a, and then a equals 0. I'll circle that. You notice, so that it didn't stop students panicking they've done it wrong and wasting time checking through your answers, in the exam question it said find the value of b and the value of c, so that's why I've circled it. B to be 1, c to equal 2. It also said show that a is 0, and we did that by using comparing coefficients, and that was part 2i as well. Right. The next part of the question is virtually, it's been asked in the chat on how you do it, but this is because it's a binomial expansion question from the second year content. You probably don't learn this until year 13, but you use partial fractions a lot of the time in the harder questions towards the later end of year 13 to either integrate harder functions or use the binomial expansion on harder functions. Now, if I just remind students, or if you're in year 12 learning ahead of time, which is always a great idea, I'm just going to remind them of the binomial expansion formula in the formula booklet that you can learn how to use. So, in the formula booklet, it's written something like this. Now, it's very rare that they go past the x cubed term because it takes a bit of time. But what I would suggest is the trick is, what you see is that the third term here, what you would have is, it doesn't write this in the formula booklet, but what you will learn is n times n minus 1 times another n minus 2. And every time you go, you keep adding well, when I say add, you times by another bracket, n minus 2, n minus 3, n minus 4, etc. But on the denominator, it would be 1 times 2 times 3. Again, if it was the fourth, second, third, fourth, the next term, you'd have to put 1 times 2 times 3 times 4, etc. And this one would be the x cubed power. Now, just remember, there's an important thing that we might or might not need, but in the formula booklet it says the modulus of x has to be less than 1. So that means this series only converges for x values in between -1 and 1. So for small x values. And remember, n can be any real number. So here, the power here, okay, can include, it doesn't have to be an integer anymore like in first year, it can include fractions and negatives now, okay. And there's an important fact also that's not written in the formula booklet that students need to remember. Just from first year, binomial expansions can be used to approximate values. And even though you can sub in x values to be in between 1 and -1, the closer x is to 0, the closer x is to 0, the more accurate the approximation. And that's a crucial fact that's tested on those 1 or 2 mark type of questions. Closer x is to 0, the more accurate the approximation is. Alright, so there's important facts about the binomial expansion, but how do we use it after using partial fractions? Well, we need to write fx in a series form of ascending powers of x. Now, we won't usually be able to do this for a complicated fraction, but if I go back to, it's just a reminder, it did say express it in partial fractions form that I will write now. I knew I was going to come to write it for part B anyway, but a is 0, so what do we have? We have, instead of writing the more complicated fraction fx, we're going to write it as b, so that's 1 over, so you've got 1 over 5x plus 2 squared, like that. But you've also got c, which is 2 over 1 minus 2x, plus 2 over 1 minus 2x. So, first things first, can we use the binomial expansion on these straight away? Well, if you compare them with the formula booklet always wants it in 1 plus form. So, first things first, they need to be a bracket to the power, so I will convert it to 5x plus 2, knowing about your negative indices, to the power minus 2, and also plus 2 times 1 minus 2x to the minus 1. That's the first thing I would do. So the brackets become, if you like, on the numerator, but with a negative power. The next thing is I would write the x term as the last thing in the bracket, because you're trying to get it in the form that the formula booklet wants it in. So what we would do is write 2 plus 5x to the power minus 2, and then plus 2, and then I'm going to write, oh, that's already in 1 minus 2x form. That's great. Now if we notice, the 2 plus 5x bracket is not one add, but you can take the factor of 2 out. But when I teach this for the first time round, what I usually recommend is put brackets and then put brackets inside them, because you need to take a factor of 2 out of both terms and take a 2 out like that. The reason why I advise you writing it like that when you start with is because a big mistake we see is people remember to take the 2 out but forget that needs to be raised to the power minus 2 as well, because everything in the bracket 2 plus 5x is raised to the power minus 2. So yes, you can take the 2 out, so it's 2 times 1 plus 5 over 2x, but then remember it's 2 to the minus 2 and 1 plus 5 over 2x to the minus 2 as well. The nice thing about the next bracket is it's already 1. If you want to put add minus 2x like that, you can do. Like so. Right, so if we simplify both these down as much as possible, we would get 2 to the minus 2 is 1 over 2 to the squared, so quarter. 1 plus 5 over 2x to the power minus 2, and then we are adding 2 lots of 1 plus minus 2x here to the power minus 1. Right, now we're in a position to use our binomial expansion formula. So the first thing it says is 1 add nx. And what I like to do is always highlight where am I using the binomial expansion. We're starting to use it here. Right, so a quarter. Now, you put the 1 down. You add n. Now n is the power, so in the first bracket it's minus 2. Now remember, do not just write x, because the x they are stated in the formula booklet is the second thing in the bracket. So the x here is 5 over 2x. And if it has a minus sign in front of it, you include the minus as well. So 1 plus nx. The n is minus 2. The x in our question is 5 over 2x. Right, I just want to go back to the exam question and double check. How many terms do we need in this question? It says in ascending powers of x, it says p, qx and rx squared. So actually you only need up to the x squared term, you don't need the x cubed term in this particular example. Right, so we only need one more term, and that was n from the formula for the binomial expansion, n times n minus 1. So it's minus 2 times minus 3. All over 2 factorial, or 2 times 1, is 2. And then remember, when it said x squared, you put our x being squared, and our x in this question is 5 over 2x, which is being squared. Remember, the squared is squaring not just the x, but the 5 over 2 as well. And then if you want to put add ... you can do. You can simplify that and then concentrate on the other bracket, but what I do is usually move to this one and then put add 2 lots of. This time it's 1 add n is minus 1, x is minus 2x, so remember the minus needs to be included when you substitute it in. Then it's add n times n minus 1, so minus 1 times minus 2, all over 2, and that becomes, instead of 5 over 2x squared, it's minus 2x that's all squared, add ... And then let's have a go at simplifying these. A quarter, 1 minus 2 times 5 over 2, x becomes minus 5x. then what you do is you do it in your calculator, but -2 times -3 becomes positive. The 2's cancel, you're left with the 3. But it's 3 times 5/2 all squared. Remember to put the 5/2 being all squared, so it's really 25/4. And you're left with 75/4 x squared, add ... You do the same thing with the other bracket. You can see why now they've asked you to put a in a 0, because it would have needed a third bracket you need to use the binomial expansion on, and it could have become quite complicated, or not more complicated, but more time exhausting. Right, so 1 plus 2x. The minus times the minus becomes a positive, and then it's -2 squared becomes a positive. But you can do it in a calculator, and it would become plus 4x squared, add ... And then what we would do towards the end, we would multiply out our brackets, because this is what another thing, after you've done the binary expansions, you can forget about the factors at the start, which is why I like to write it all out step by step and then simplify it, rather than just doing a bracket then a bracket, because it can mean you forget to times by the quarter and the 2 at the start of each bracket. So you've got a quarter, you've got -5/4 x, you've got plus 75/16 x squared, add ... and then add 2 plus 4x plus 8x squared, add another ... And then you can correct the like term. So you've got quarter plus 2 is 9/4. The -5/4 add 4, or 4 minus 5/4 is 11/4. So you're left with add 11/4 of x. And then 75/16 plus 8 is 203/16 x squared, and that you could put add ... And if p and q are constants to be found, p, q are simplified fractions. Let's check them. So p equals 9/4, q equals 11/4, and r equals 203/16. Is simplified fractions. Right. But at this point, I would go back and check my working just to see if I've made any mistakes. It's quite possible you do, and in an exam, they're the ones that take up a lot of marks because of the time they can take. I just want to make a point right at the very end of the exam question. It says, find the range of values of x for which the expansion is valid. Well, I said this is where you need to remember these two important facts about the closer x is to 0, the more accurate the approximation is. And also, x needs to be less than 1. Now remember, that was the original x, in other words, the second thing in the bracket you use the binomial expansion on. That is not our x in our question, because this is why I underlined when we use the binomial expansion. Here it was, okay, 5/2x needs to be less than 1, or the modulus has to be less than 1. And also we use the binomial expansion a second time on this bracket. -2x, the modulus of it has to be less than 1. So if we take both of them and rearrange them, the first one becomes the modulus of x has to be less than 2/5. You can ignore the minus in the -2x, because when you do the modulus size it becomes positive 2x. But this one refers to x being, or the modulus of x being less than 1/2. Now for us to use the binomial expansion we needed both brackets to work, because we used the binomial expansion on each individual bracket. So you need both of these to be satisfied. So that's why you always choose the smallest one. 1/2 is about 0.5, is 0.5, 2/5 is 0.4, so you would choose the x to be less than 2/5. You use the smaller one, okay? Because then they would both work, not just one of them. If you chose a half or something in between 0.4 and a half, then it would work for the minus 2x less than 1, but not the 5/2x less than 1. Right. So you can write it in two different ways. You could write the modulus of x to be less than 2/5, or it used to be called the radius of convergence. I've got out of the habit of using that terminology now. But if you want to write that, you would put x's being between 2/5. And because it's the modulus is less than 2/5, x can be negative, yes, but it needs to be bigger than minus 2/5. So that's the type of thing we would write. Right, I'm just checking the chat to see if there's any more questions. I know it's getting to the end of the academic year, well, the very last one actually. But I would just see, and I've got an email here that's also asked me about, can we go through this question? They will watch the live stream later. And this is a GCSE question to do a bit of practice on. Right, so this looks like a typical bounds question. Okay, you've been given a formula, y equals 2a over b minus c. You've been given a equals 42, but when it says it's correct to two significant figures, it's not actually 42 exactly, it's nearly 42. And when you see these type of questions, the first thing you should do is write an error interval for each value. So a is between, if it's 42 to correct to two significant figures, the 2 is the second significant figure, so it's the digit after you have to increase by 5 or lower it by 5. So it's definitely less than 42.5 and above 41.5. If you want to be absolutely precise, technically the left side of the error interval is greater than, well, a is greater than or equal to, because it can include 41.5 because that would round up to 42, but it cannot include 42.5 because that would round up to 43, and we know a is rounded to 42 to two significant figures. Always check the next two lines just to check if it's the same significant figures, because they have done in the past where they've rounded it to different values. But in this particular question, b is very similar. It's between 24, well, it's lower than 24.5 but higher than 23.5, and also c is between 14 or 13.5 and less than 14.5. So the first thing you do in bounds questions is you write an error interval for each value that has been rounded. Then you write down the formula, because sometimes if you're tackling a worded problem or a problem to do with right angle triangles or that type of thing, the formula won't be given, but you can design a formula. Okay, but here you have y equals 2a over b minus c. That is the formula. The reason why the formula is so important is we are not doing a degrees of accuracy question where you need to consider both lower and upper bounds and state which is or what y is to a certain degree of accuracy. We only need to find the lower bound, but it's not always the case where you sub in just the lower values for each a, b and c, because you need to know about your operations. Okay, so in other words, y is a fraction here. So how would you make, okay, this larger? Oh, sorry, it's a lower bound, so you're trying to make it the smallest y can possibly be. So how would you make this smaller? So what you need to remember is when you're writing a fraction, to make a fraction as small as possible, you need to make the numerator as small as possible. So you need a lower bound for 2a. But the big thing you need to remember is if you're making a fraction smaller, you need to, if you're thinking about you're dividing it into this many pieces, if you only divided it into one piece, the whole answer would be quite large. But if you're dividing it into many pieces, a lot of pieces, the answer becomes small. So you do the opposite on the denominator as you would to the numerator. So you need to make the denominator as large as possible. So what you need is an upper bound for b minus c. Okay, you can see why this one's quite tricky, because it's not just a case of subbing in like the largest b and c. It's because the denominator's b and c, so you have to make this. Okay, so you need to try and find an upper bound for b minus c. And it's a similar thing. If you're adding two things together to make them as large as possible, you just make them as both as large as possible. So b, okay, I'm going to choose an upper bound because you're trying to make this result as large as possible. So an upper bound for b, as we've said, is 24.5. That's the highest b can be. Right, so we'll put 24.5. But because you're subtracting c and you're trying to make the answer as large as possible, you're trying to subtract the smallest amount that's possible, because subtraction, just like division, you have to do the opposite of what bound you are trying to find. So here you have to do a lower bound for c. Because the idea here is to find the highest b minus c can be, you increase b to its maximum, but you want to take away the smallest amount that's possible. So you need to reduce c as low as it can be. So the lowest value for c we've seen from our error intervals is 13.5. So we need to choose 13.5. And if you want to be technical about your error intervals or your inequality signs, the reason why you cannot put less than or equal to is because even though c could equal 13.5 exactly, b could not equal 24.5. So you can only put the equal sign if both values you are subbing in can be equal that value exactly. Okay, because I'll just put that here, because at least one of b and c is not including so it's not less than or equal or greater than or equal. Right, so yeah, if we just want, you can do these in a calculator. Usually the bounds questions are in a calculator, but 24.5 take away 13.5 is equal to 11. So going back to the question at hand, b minus c, as we've said, is at most 11. So 2a over b minus c. You're trying to find a lower bound, so you're trying to make it as small as possible. So that means you make 2 times. When you times things together, you just times the smallest ones together. So it's 2 times the lowest value for a. So the lowest value for a is 41.5. And as we've said, to make the fraction as small as possible, you need to make the denominator as large as possible. So we need to make b as large as possible, 24.5, and c as small as possible, 13.5. So yeah, that became 11. So if we do that and multiply 41.5, 2 times 41.5 divided by 11, you would get 83 over 11. Or, it depends on how it wants it as an answer. You could leave it in exact form, but you won't get the final mark because it specifically asked you for 2 significant figures. So divide 83 by 11 and you'd get 7.5454, etc. ... 2 significant figures. The first, the second is the 5. The next number is a 4, so you don't need to round up. So you'd put 7.5 and a lower bound for y. Again, you won't get penalised. Well, on the mark schemes you don't get penalised for this, but okay, you don't include it. Okay, include this value. And why don't you? Because we used at least one value, A, B or C, where it couldn't equal. Could A equal 41.5? Yes, so that was okay. But when we subbed in the value, was it the B or the C value? Okay. B was 24.5 that we used, and B cannot equal 24.5 there. Okay. So because one of the values it cannot equal, the final answer cannot equal that exactly. So that's a bit of a bounds question for those higher GCSE students needing that bit of help. Right, so that brings me back to the final things I want to mention about this academic year. These streams have been new for me for this year. I hope people have found them useful. We're looking to take them on to a next level with helping as many students as possible over the course of next academic year. We'll be looking to start them again in September. I hope people have benefited from them, and I hope you're all pushing forward for your highest possible grades. You can succeed in either your Year 11 exams or your Year 13, or even if you want to start early from Year 8 and 9 to start revising and practicing for your GCSEs. Everyone is welcome. Next year, these streams will probably be on YouTube, or they will be on the members area of my website. The website is not up and running fully yet. We've got the sort of main profile page, but we've not got access to streams. So hopefully this will be done over the course of August and they'll be up and running for September. If not, they'll be back on YouTube. But it all depends on how quickly my website gets developed. So these streams will not go over the summer holidays, but they'll be back again in September. I hope to see you then. If Year 11 and Year 13s are looking for extra revision practice, I recommend you do bits and pieces of important topics. Now, it's important to get a rest over the summer holidays. Take at least a couple of weeks off to feel refreshed and recharged going ahead into the important Year 11 or 13, because I know your exams will be sat then. And you don't want to be feeling burnt out after the summer holidays, because once September starts, you won't get much of a break or a lengthy break after that. So yes, take a break, but if you want to do 3 or 4 weeks where you're dipping your head into individual topics, do small amounts but at a fairly often rate. So let's say you don't do more than 1 or 2 hours a day, but you want to do an hour here one day and then a couple of days later do an hour there. That's perfect. Focus on the most popular topics. They are quadratics, recurring decimals if you're doing GCSE, trigonometry if you're doing GCSE, or A levels. The trigonometry identities are very important. Radians, differentiation. Try and revise the first year content by doing the AS papers. That's what I recommend. But keep pushing. Do bits and pieces now and again, and get into the habit of learning what you feel comfortable with on exam papers, and what you do not feel so comfortable on, and then they're the topics you need to focus on, sort of in particular going forward. And I'll be happy to help you with any questions you have when we start the new academic year, or message me in the meantime if you feel you're banging your head against a brick wall. That's what I'm here for. I'm always happy to help. Right, so yes, all I have left to say is I wish you a very brilliant summer break wherever you're off. If you're on holiday, then I hope you enjoy the sunshine somewhere. If you're off on a staycation, I hope you have a brilliant summer, and I look forward to seeing you again after the summer holidays. See you in September.